Welcome back to NET Physics series. Today we'll continue with chapter number 7, which was of oscillations, and this would be a part 2 and the final part for the topic of oscillations. So let's start with this topic, which is of the motion of projection of a body which moves in a circle, right? So this motion of projection of a body which is moving in a circle on a diameter with a constant speed, so speed must be constant. This implies simple harmonic motion, right? Now, for such type of emotion, the acceleration is given as minus omega squared times x, where x is the displacement while omega is the angular velocity of the motion. And so the time which it takes to complete one round on this circle is given by 2 pi, which is the total angular displacement that it would take. So for example, if this is your point, you start at this point and you move a distance like this. So what you're doing is you're coming back to this point, which is moving an angular displacement of 2 pi radians, right? Or you can say you moved 360 degrees in angular displacement from coming back to this point P. Hence, the time period is given as this angular displacement divided by the which with what velocity, which would be the angular velocity, is this angular displacement covered. So that's omega. So that's the time period of this projection. So you can then find the speed of the projection, which is the linear speed, and this speed of the projection, let's denote it by v, or let's write this curly v. It is given as the angular velocity, the angular speed, times the square root of r squared minus x squared. Now, r is just the radius from the center of the circle to this point P, the at to the circumference, right? So that's the radius of the circle, and x is any displacement, linear displacement, right? So the radius of the circle r is also the amplitude of my oscillations, right? Now you can also say this thing is the amplitude of the simple harmonic motion, right? So now this projection that we're talking about, it will increase. So we have that the projection of this body increases if our body is moving towards the circle. For the body moving towards the center of the circle, right? And the projection will decrease if my body moves away from the center. Now, the reason for that is that if you remember what we studied in circular motion, we had that the force in a circular motion, the force that is responsible for keeping your body in towards the center of the circle, was mv squared over r. So from this expression, it is clear that force is inversely proportional to r. Now, if R increases, that means the force would decrease. And if the force decreases, that means the acceleration would decrease. Hence, the body would start decelerating and the projection speed would decrease if the body moves away from the center, right? So if R increases, that means that the body is moving away from the center. Similarly, if R decreases, so if the body is moving towards the center, then this would imply that the force from this expression would increase, and hence the acceleration would increase, which would mean that the speed would increase, right? And in this case, the speed was decreasing. So that's the reasoning behind this. Now, one of the most important conditions for SHM is that omega has to be constant. Now, this omega is just the angular speed of the body, which is in circular motion, and that has to be constant for the projection to have SHM. Now, if it were not constant, if the angular speed was not constant, then that would imply that we have a completely vibratory motion, which would not be an SHM, would not be simple harmonic motion. So I should write it would be a non SHM motion. Right. Now let's move our attention to what is called a simple pendulum. Now, a simple pendulum consists of a mass which hangs from a rigid point. So you can say from here, and it hangs by the means of a string, and this string is so thin that this string is almost weightless, right? So we can assume it to be weightless. So it has almost a negligible mass. And the assumption is also that this string should be, let me write it like this. So it should be inextensible, right? What that means is that it should not be elastic, or it should not be extendable, right? Okay, so now this idea or this whole thing was basically invented by Galileo, the idea of a simple pendulum. And the motion of this pendulum is simple harmonic motion as long as there is no damping in the simple pendulum. Now, damping is just a frictional resistance or force in this system, and we'll discuss it in a few minutes, right? Or what we can do is we can just start off by discussing the damping, right? So damping, basically, it's you can think of it as a force. It's a force, and its aim or its goal is to reduce the amplitude of your motion, right, or your oscillation of the simple pendulum, and it will reduce this amplitude continuously, right? And it will keep on reducing this amplitude, the damping force, until the motion is stopped, right, until the body comes to rest, right? Okay, so now a motion, you can assume a motion to be independent of this damping force, and in that case the damping force would be absent, So in the case of absence of this damping force, what would we have? Well, basically, in the absence of this damping force, the restoring force would be given as what? Well, again, think of this pendulum. So, for example, you displace it like this. This is your bob with mass m, and this is the normal from this point. So, the weight of this mass would be like this, and the restoring force, or you can say that the tension actually in the string is something like this, and the restoring force is in this direction, the one that would be keeping it uh, going towards this mean position. So the only component, if I draw this thing as well and the angle theta is over here, then this component is the, or you can just let's call this f. It would be f sine of theta. Now just give me a second, 1 second. So the idea basically at this point is to first define your coordinate system. And we'll define, it turns out that it's easier to define a coordinate system that is kind of tilted basically. And you can define it like this, right? Where this is your plus y and this is your plus x. Now we define our coordinate system in this way because at most of the time that we're dealing with this simple pendulum, it would be oscillating in this position, in this manner, and hence it's easier to define a coordinate system which is kind of rotated from your original coordinate system, right? Which is looks something like this, but instead of this we'll use this one, again for the reasons described. So in this case then the restoring force is actually this one. Let me draw it. It's something like this. It's not really a straight line. It's and now it's towards this direction. Our positive x is in this direction, so it's towards the center, and it would be minus, and it would be the sine component of this force, which is mg. So it's minus mg sine theta, where theta is simply this angle from the normal, right? The angular displacement that we produce. And hence the restoring force, let's give it Fr subscript, it would be minus mg sine theta. Now suppose that this angular displacement is very small. So in that case, we know that sine theta is just theta, right? For small theta. So in that particular scenario, if the angular displacement is very small, then the restoring force acting on the system is just minus mg theta, right? Now the uh, you can you can box this equation. This is for a small angular displacements, right? Now the acceleration for such displacements, small displacements, is then given by minus g over L times x. Now recall that the acceleration of a simple pendulum or the acceleration in simple harmonic motion was given as minus omega squared x, right? So basically, if this simple pendulum were a simple harmonic motion, then these two accelerations should be equal, right? So this acceleration should follow this uh, acceleration for the simple harmonic motion. So that case, comparing the two equations, we see that omega squared is equal to g over L, which means that the angular velocity is given as square root g over L, right? So for a simple pendulum, this is the angular velocity, and you can see that this is independent of mass, and it is also independent of the amplitude. Now, having this at our hands, we can write down the time period for such a system as 2 pi over omega, but omega is square root g over L, so it becomes square root L over g because omega is in the denominator. So that's the time period for a simple pendulum. Now, having time period, we know that the frequency is simply given as 1 over time period. It is the inverse of time period. And so the frequency of the oscillations is then 1 over 2 pi times square root g over L, which is just 1, you can say it's just omega over 2 pi. So that's the frequency of the oscillations. Now, if suppose let's do we have more space on this page? No, let's go to the next page. Now suppose that if you have a pendulum and it is suspended in a lift or an elevator, then you would have two cases, one of which is, so if you have a pendulum that is suspended in this lift which is moving upwards or ascending upwards with the acceleration a, then note that this acceleration a should be uniform or constant. Then the time period is defined as 2 pi square root. So everything remains the same except you add this acceleration a to this g. Now the other case could be the descending down case. So you have a pendulum which is suspended in this lift, and this lift is moving down with some acceleration a. In that case, the time period is given as 2 pi square root L g minus a, right? Now, one may note over here that this time period does not depend. How do I write it? So we can say the time period is independent of mass m and the amplitude of the oscillations, right? Now, as for a simple pendulum, typically we have the time period as 0.2 seconds. The frequency is given as 0.5 hertz. You can find that from the time period as the inverse of time period. And the length is normally about 1 meters. It's about 1 meters. Well, or you can say that it's, let's give it a range. It's normally from 0.99 to 1 meters, right? Wonderful. Now let's discuss quickly the conservation principle for energy in a simple harmonic motion. So the kinetic energy of a simple harmonic motion is given as, or you can say that the instantaneous kinetic energy at any point x is given as 1 by 2 k x squared, right? You actually, this k is the spring's constant, right? Or it's just a constant, and this x is the x naught squared. So x naught is basically the displacement or the mean position, right? And then you have this another factor, which is 1 minus x squared over x naught squared. This factor appears, or this second term specifically, this one appears if you are talking about instantaneous kinetic energy. So the maximum kinetic energy is half k x naught squared. And again, the reason for this is that if you have this spring mass system, when I extend or pull this mass towards this side, then it gains some potential energy. And when it's coming back to its mean position to the left, when it reaches its mean position, at that time, all of that potential energy is converted to its kinetic energy, and hence the kinetic energy at this mean position would be maximum, right? Okay, so that's the kinetic energy, which is maximum, and it's at the mean position. While at any extreme position, uh, at any extreme, which would be, for example, if I extend this spring and I bring it over here, and now I'm releasing it from this point, right? So it would move here, but the point from where I release this mass is the extreme position. And so when I have my mass at that extreme position, which is over here, then there is no kinetic energy. You only have given it maximum amount of potential energy, and now you release it, and that potential energy starts getting converted while it's moving to its mean position to the kinetic energy. And when it comes to its mean position, then the kinetic energy is maximum. So at the extreme position, the kinetic energy simply vanishes. All of the energy at that point exists as the potential energy of the system. So this would be the minimum kinetic energy, which exists at the extreme position. And so then we can also talk about the potential energy of the system, which would be the instantaneous potential energy is simply half kx squared. Now note that I don't have any x naught in this expression, and the reason for that is that at its mean position, you have not displaced it, which means you have not given it any form of potential energy that it can store in the system. So there is no stored energy in the system, and hence there is no x naught would not appear. In fact, at x naught, the potential energy would vanish. So the maximum potential energy that I can provide to my system is simply half k. And now let's just give this x, let's call it x1 squared. Now this x1 is the displacement of this mass at some extreme position. So for example, the mean position was here, and now this is the displacement from that mean position. So that's x1, and hence the potential energy would be maximum at that extreme position, and it would be minimum, which would be 0 at its mean position. So again, from the conservation of energy, the total energy of my system, which is half k x naught squared, this should be conserved in SHM, right? So that's the conservation of energy, and this is the total energy of the system, which would be conserved in simple harmonic motion. Moving on, let's discuss the topic of resonance. Now, what is resonance? Basically, resonance is defined as a phenomena of an increase in the amplitude of a body which is capable of vibrating, right? Under the action of a periodic force. So, a force which is periodic and it acts on the system and increases the amplitude of the system, whose time period is just the same as the natural time period of the body. Now, this whole thing can be thought of in multiple ways. You could have also said the same thing in this fashion, that a response of a system to any external periodic force whose time period is equal to the natural time period of the body is known as resonance. Or also, you could have said that resonance is a process in which a body would transfer all of its vibrations to a body that's near it. So, for example, you have this thing, and then you have another body which is this one. And so, if it's vibrating, it would transfer its vibrations to this body, and it would start vibrating, but only if the natural time period is agreeable to this body as well. So you can think of molecules or atoms which are vibrating, a chain of atoms on a lattice, and they're vibrating, so uh, they transfer their energies or vibrations to each other, right? So that's the case. In fact, resonance is the cause of you getting tired when you start walking very fast, right? So, if you're walking very fast, then because of resonance, you are going to get tired. Because what happens is that when you start running fast, or you can say in an active manner, in that case there are you're causing forced oscillations, and these oscillations are fed into your legs, right? So these forced oscillations, which are periodic in nature, and so they cause resonance, and hence you feel more tired by being in an actively running or walking manner. This is also a resonance is a reason where if you own a vehicle, and if there are loose parts in this vehicle, so for example, you have there is a door, right? So there is a door over here. Ignore my drawing. And so for example, in this door you have some parts, right? You have a handle, you have inside the door, you have an armrest and everything. Now if the parts are loose, then they're going to be more noisy, and at when you attain a particular speed in your vehicle, they're going to be more noisy, and that's also due to this resonance phenomena. Resonance is also a reason that a microwave oven cooks food, right? So if you have a microwave oven and you have the food that is in there, the microwave oven is going to generate high frequency waves, right? And these waves are going to heat up uh, in your food. What these waves do is they heat up the water and fat molecules. So heating up these molecules, uh, it does so by a large amount of energy which is absorbed by water and the fat molecules. right? And that energy is the energy of these microwaves that is being emitted by the microwave. And so the food inside the microwave gets cooked. Now we'll end this with a few properties of resonance. It's also known as the sharpness of resonance. And so basically what happens, for example, consider that you have a damping force. It would, as we discussed, it would reduce the amplitude of the oscillations. And if there is no damping, so you call it undamped oscillation, and in that case the amplitude will remain constant. And uh, if I have a damping force which is small, so a smaller damping force would in turn produce a sharper resonance. This sharpening of the resonance, or the sharpness of the resonance, is basically defined, or it explains how fast the energy is going to decay in a system which is oscillating. So the more sharper the resonance, the faster this decay of energy will happen. And it depends on the damping, right? So the smaller the damping, the sharper the resonance, and vice versa.